In this lecture, we're going to talk about how we find the quantitative amounts of various phases in a multi-phase sample. This is taken from chapter 2 and Lang, specifically the section 2.3.4.2. So we can get the quantitative amounts, the relative amounts of the compounds or phases in a mixture, and we can do this by the intensity of the diffraction peaks in that phase and compare them to one another. So the intensity of diffraction peaks depends on the weight fraction of the particular phase. So we're going to use this fact to determine the weight fractions. So we can express this as the intensity of a phase I is equal to the term K times Ci over mu m. So this is the peak intensity of the phase I. C sub I is the phase I weight fraction. And then K, which I'm running out of space here, sorry about that. K is constant related to the X-ray source. So that would mean wavelength, incident angle, and the incident intensity. The last thing I want to mention is the mu term here. This is the linear absorption coefficient of the mixture. So we're using the subscript m here to represent a mixture. So everything else is for the phase, and then this constant is tied to the X-ray source. All right. One other thing I want to make about this point I want to make about the intensity here is that the peak intensity, that could mean a number of different things. But here, this is what we call the integrated intensity. And so when I mean integrated, I'm talking about if we have a peak, we're talking about the area underneath the curve. So we're really looking at peak area. And so you can integrate underneath this, that's obviously an option, or you can approximate it by taking the full width half max B times the peak intensity. So that's the maximum peak. So again, if we're going back to a sketch here, this is B, and then the max intensity, that is the peak. So we can multiply those to approximate the integrated if we can't find that directly. Okay, so we're going to talk about three methods that we can use to do this quantitative analysis that we're talking about. The first is an external standard method. So for this, we this method needs peak intensities of a particular phase in its pure state. So this isn't always available, so there are other options. One is the internal standard method. This requires a series of standard mixtures. In which the particular phase contents are known. So that's another way. So we basically make a series of standards for that particular phase with the known amounts, and we compare it to what we have. And lastly, what we're going to talk about is the direct comparison method. So this doesn't have either of these restrictions. So here, as it kind of implies in the name, directly compares the peak intensities. Between the phases in the mixture. So let's say we have a mixture of alpha and beta. So those are our two phases. The peak intensity of alpha, using this direct comparison method, is K2 times R alpha times C alpha over mu mixture. So basically this K term that we had, excuse me, this K term that we had becomes K2 and R alpha. So we separate it out because K2 is related to the X-ray source, and R alpha is related to angle and crystal properties. So basically this should be a constant, whereas this will depend on the particular phase. So we want to separate them out, and you'll see why we do this here in a second. Okay, so the R term, the R alpha term that we talked about, it's related to angle and crystal properties. So we can write this as should be V squared, and then we have the structure factor, absolute value of that. We have a term P, then we have a term involving the angle, and then a last term, which is an exponential of 2n. Okay, so again, we're saying that this is related to angle and crystal property, and we can see why with this. So this is the structure factor for the particular plane that we're evaluating. This term, kind of the lowercase v, is the unit cell volume, so of the crystal. And then we have this, which we call the temperature factor. This can be found, like a lot of these, in the tables that I've uploaded to Canvas. And then P, we call this the multiplicity factor. So this is the number of crystal planes that we have with the same spacing. So this kind of accounts for the different permutations of a given type of plane. And the last one, the angle term, this is known as, specifically known as the Lorentz polarization factor. And sometimes that's abbreviated to LP factor. So again, this is often tabulated, but as you can see, if you know the angle, we can directly calculate that as well. So it's both in the it's both tabulated in the Colody text, but also you can solve directly for it if you know the angle. I will say that the textbook, I believe, has an error in this equation, so double check to make sure that this LP equation looks good. If it's different than your textbook, again, they have an error there. You can also, if you want to verify, you can check an online source and see to make sure that they get the same thing that we do. Okay, so all of this is the R term, and that, remember, goes back into the intensity equation. So if I rewrite that for the beta phase, I would get everything. This is the same because it's for the mixture. This is based on the X-ray source, and then these two terms are related to the phase. Okay, so here I've put up a graph from our textbook, figure 2.27. This shows the temperature factor, that exponential term that you saw. And so the temperature factor is also a function of angle. And so we see here that temperature factor starts at 1 for value 0 and then decreases as we get higher, or as the angle term here gets lower and lower. So you can basically determine the value graphically from this figure here in the textbook, and it's also somewhat tabulated in the appendices that I've uploaded to Canvas as well. All right, so we've got the intensity expressions for both phases, and so now we're going to see how the direct comparison method works. So if we look at the ratio of intensities for those two phases, they're going to be equal to, so if we just plug in the equations here, we're going to see that this term and this term are constants for this experiment if we're using the direct comparison method, and so they cancel out, and what we're left with is this expression of R's and the concentration, the weight fractions. So if we know the intensities from integrating the area underneath the curves, and we calculate the R value based on structure factor, unit cell volume, angle, multiplicity, temperature factor, then we can determine the weight fractions C alpha and C beta for this phase. And so that's excuse me, and so that's the way that we can calculate those if we know the other information here that we've gone over. So that's a pretty powerful expression to be able to do that, and to be able to do that without having to do separate standards, either a pure sample or a mixed series of standards. So this is a pretty powerful method to be able to get these weight fractions from an X-ray diffraction pattern.